Unfortunately, there's a slight stumbling block that we have to be aware of when we're dealing with rational equations and radical equations actually, but we'll worry about that later. Right? There's something called extraneous solutions. Okay? An extraneous solution to an equation is a solution or a possible solution that doesn't actually satisfy the original equation. Okay? So let's look at an example to help make this more clear. All right, let's solve the equation x over x minus 4 minus 5 equals 4 over x minus 4. The first thing to notice is that the only denominator we see in this equation is x minus 4, so it has to be the LCD, right, since it's the only one. So what we're going to do is hit every term in this equation by the LCD. So I'm going to take x over x minus 4 and multiply it by x minus 4. Well, the x minus 4 is reduced, leaving me with a 1 in top. Then I'm going to take negative 5, the next term, and multiply it by x minus 4. In this case, there's nothing to reduce. All we can do is distribute the negative 5 to help us isolate x later on. On the right side, I have to multiply 4 over x minus 4 by the LCD, and again, the x minus 4's reduce away and leave me with 1. Okay. When all the dust settles here, we have a 1x left over from the first term, right here. We have a negative 5 times x and a negative 5 times negative 4, leaving us with negative 5x plus 20. And then finally on the right side, 1 times 4 leaves us with 4. At this point, we can collect our like terms, get the numbers on one side, yada, yada, yada. This is a linear equation, right? We've been solving these forever. So in the end, we end up with x equals 4. Now, you may be tempted to circle this. You may think this is the final answer. But let's look more deeply. Okay? It turns out that x equals 4 is actually an extraneous solution to this equation, not a real solution. Okay? Because if you substitute 4 into the original equation for x, you get something kind of fishy. All right? So focus on this original equation here. X over x minus 4 minus 5 equals 4 over x minus 4. Okay, and substitute in x equals 4. So it's going to become 4 over 4 minus 4 minus 5 equals 4 over 4 minus 4. Well, 4 minus 4 is 0, so you're getting division by 0. Not good. Right? We don't know how to divide by 0. Okay, so x equals 4 can't be a solution to the original equation because it gives you some undefined expression. All right? So the only possible solution we found doesn't make sense in the original equation, so there's actually no solution to this equation. So there's a very important conclusion to draw from the last example. When solving rational equations, you always have to exclude any solutions that make any denominator in the original equation 0. Right? If you look back at our solution, or our proposed solution, to our equation in the last remark, we solved the equation x over x minus 4 minus 5 equals 4 over x minus 4 and ended up with the solution x equals 4. But this doesn't make any sense because this 4, when you plug it back into the denominator, either one actually, is going to make the denominator 0, making the fraction undefined. Okay. So always exclude any solutions that make any denominator in the original equation 0. So we said, all right, this is not a good solution, which left us with no solution as our result because there weren't any other options. So keep this in mind when you're solving rational equations. So here's our last rational equation. We have to solve x over x minus 3 plus 4 over x plus 3 equals 18 over x squared minus 9. Now, the strategy to solve an equation with fractions is to clear the denominators by multiplying by the LCD. To find the LCD, you have to look at the denominators, factor them if needed, right? So x minus 3x plus 3 can't be factored, but x squared minus 9 can be factored since it's a difference of squares. This is x minus 3, x plus 3. Right? And then you take each factor the most number of times it occurs in any single denominator. In this case, our LCD is going to consist of just the factors x minus 3 and x plus 3. Right? From this denominator, we need an x minus 3. From this denominator, we need an x plus 3. And then we have this guy covered, so we don't need anything extra. Right? So this is what I have to multiply both sides of my equation by. So let me do it. So this is what it looks like after we hit each term in our equation by the LCD. Remember, this is in the numerator. You can think of the LCD as x minus 3 times x plus 3 over 1. So then we want to reduce any like factors. For example, in this first term, the x minus 3 and the x minus 3 reduce to 1. In the second term, the x plus 3 and the x plus 3 reduce to 1. And in the last term on the right side, both the x minus 3 and x plus 3 reduce with the LCD. So all of our denominators left. Here we have x plus 3 times x left over. Here we have 4 times x minus 3. And then finally we have 18. So let me write our new equation out. At this point, all of our denominators are gone, right? We reduce them away by multiplying everything by the LCD. Okay? But we actually don't have a linear equation here. Right? When you multiply out this x, when you distribute it, hopefully you see that you have a quadratic equation, because this is going to give you an x squared plus 3x. Then let's go ahead and distribute here while we're at it. Plus 4x minus 12 equals 18. Okay, so because of this x squared term, we know we're dealing with a quadratic equation at this point. And the strategy to solve a quadratic equation is to get one side to 0 and either factor or use the quadratic formula. Right? So let's do that. So after collecting like terms, 3x plus 4x is 7x, and after subtracting the 18 over to get one side equal to 0, here's my quadratic equation. X squared plus 7x minus 30 equals 0. You could use the quadratic formula on this if you were so inclined, but I wouldn't suggest it. Okay, if you look at your factors here, if you try to factor this, the 1 in front of the x squared is 1 and 1. And the 30 is either 3 times 10 or 6 times 5. But we can stop right there because I already see a combination of factors 3 and 10 that I might be able to get 7 out of. Okay, so I can factor this using my box. Here's the box, here's what it looks like. You use 3 and 10 to combine to 7 in the middle, but multiply to negative 30 on the end. And the factors end up being x minus 3 and x plus 10. Okay, so the only way x minus 3 times x plus 10 can equal 0 is if each individual factor equals 0. I'm running out of room, so just let me give you the solutions here. If x minus 3 equals 0, then x has to equal 3. And if x plus 10 equals 0, then x has to equal negative 10. So these are our possible solutions to this rational equation. It took us a long time to get here, but there they are. We have to be careful still, though. Okay. Do x equals 3 and x equals negative 10 both work in the original equation, or are they extraneous solutions? X equals 3 is highly suspicious, right? If you plug x equals 3 into this denominator here, you will get 3 minus 3, which equals 0. That is bad, right? X equals 3 gives you 0 in the original equation in the denominator. That's an undefined fraction. This is an extraneous solution. We cannot include this solution in our solution set. X equals -10 is not a problem. If you plug -10 in here, you get -13. Here you get -7. Here you get, 91. X equals -10 is not a problem. X equals 3, however, is a problem. So we cross that out. We do not include x equals 3 as a solution, but we do include x equals -10.